FEM philosophy simplified. The philosophy of FEA can be explained with a small example such as measuring the perimeter of a circle. Here, a circle is shown. If you want to calculate the perimeter of a circle using our conventional formula 2 pi r, then we know how to calculate. That is the analytical method. But in FEA approach, we will divide that circle into a number of segments as shown in the figure. Then joining the points using straight line. Since it is very easy to measure the length of a straight line, we will measure the length of one line and then multiply by the number of segments. In this figure, 8 segments are there. So length of one line into 8 will give the perimeter of the circle. But that result will not be an accurate result like 2 pi r. It will be an approximate result. To increase the accuracy, what we will do, we will increase the number of divisions on the circle. Say for example 25. Then we will get more or less accurate result like the value we get from 2 pi r. Based on application, the finite element problems are classified as structural problems and non-structural problems. In structural problems, the displacement at each nodal point is obtained. By using these displacement solutions, stress and strain in each element can be calculated. For example, stress and strain in trusses, stress and strain in machine parts, etc. In non-structural problems, temperature or fluid pressure at each nodal point is obtained. By using these values, properties such as heat flow, fluid flow, etc. for each element can be calculated. There are two general methods in structural FEA. In this topic, we will study only structural problems because that is more simple compared to other methods. The following two general methods are associated with the finite element analysis. They are force method and displacement or stiffness method. In force method, internal forces are considered as the unknowns of the problems. In displacement method, displacements of the nodes are considered as the unknowns of the problem. Among these two approaches, displacement method is more desirable because its formulation is simple for most structural analysis problems. So, for our study, in the coming classes, we will be studying about displacement method only. FEM in structural analysis. The procedure. The general procedure in FEM structural analysis. First step is divide the structure into pieces. That is known as discretization. Then describe the behavior of the physical quantities on each element. Connect or assemble the elements at the nodes to form an approximate system of equations for the whole structure. Then solve the system of equations involving unknown quantities at the nodes. Unknown quantities, example, displacement. The last step is calculate desired quantities. For example, strains and stresses at selected elements. So this is the general structure of an FEM analysis procedure. Detailed steps are coming in the coming classes that we will see. Now we will go to the broad chapter, general steps of the finite element analysis. These are the steps. There are 3 steps. These are pre-processing, analysis and post-processing. And each of these 3 steps are divided again as shown here. Under pre-processing, we have discretization and numbering of nodes and elements. After that, analysis starts. In the analysis, solution of the displacement function, define the material behavior, derivation of element stiffness metrics and equations, assemble the element equations, applying the boundary conditions, solution of unknown displacements, computation of the element stresses and strains. These are the steps in the order. Then the last step, which is coming under post processing, is interpreting the results. We will see each step given in the figure one by one. Step 1 is discretization of the structure. We are already seen what is we have already seen what is discretization of a structure. The art of subdividing a structure into a convenient number of smaller elements is known as discretization. These smaller elements are classified as follows: one-dimensional elements, two-dimensional elements, and three-dimensional elements. Let us see what are these elements. First, one-dimensional elements. A line is the simplest one-dimensional element. These are used to represent rods, beams, trusses, frames, etc. Two-dimensional elements. Triangular and quadrilateral elements are the simplest in this case. They can be used to represent plates, shells, etc. These elements are loaded by forces in their own plane. Next is three-dimensional elements. The most common three-dimensional elements are tetrahedral and rectangular prism or hexahedral elements. These are shown in the figure. These elements are used for three-dimensional stress analysis problems. The discretization of a two-dimensional structure is shown here. It is discretized with a triangular element as shown in the figure. The second picture, same kind of discretization but with smaller triangular elements. Total there are 912 elements compared to 228 elements in the first case. Step 2 is numbering of nodes and elements. The nodes and elements should be numbered after the discretization process. The numbering process is important since it decides the size of the stiffness matrix and it leads to the reduction of memory requirement in the computer. So in the first picture, numbering of the nodes are shown, only the numbering of nodes for various element shapes. In the second picture, numbering of the nodes and elements are shown. Elements are numbered in blue color and nodes are numbered in the red color. The numbering of nodes and elements need not be studied in details now because most of the softwares are doing it automatically. Now step 3, selection of displacement function or interpolation function. In this step, a displacement function or interpolation function is selected. For each element, there will be a displacement function. Usually, this displacement function will be a polynomial. It can be a linear, quadratic, or cubic form polynomial. These polynomials are used because they are simple to work within finite element formulations. Here we can see polynomial approximation in one dimension. In this graph, we can see how a polynomial is used for linear as well as quadratic approximation. The dotted line represents the linear approximation in the first picture A. Linear approximation means it will approximate the exact solution with a line. The equation is phi x equal to a0 plus a1x. Only x is the variable, so it is a linear approximation. In the second figure, that is B, quadratic approximation can be seen. It is more or less near to the exact solution. Exact solution is the bold line and dotted line is the polynomial approximation. In quadratic approximation, a quadratic polynomial, that is phi x equal to a0 plus a1x plus a2x square is used. So it is more convenient to approximate the exact solution. If you use a quadratic approximation instead of linear approximation, we will get a much better approximate solution, much better accurate solution as shown in the figure. Why polynomial type of interpolation functions are used in FE analysis? The answer is this. First one, it is easy to formulate and computerize the FE equations. Computers can easily formulate polynomials. Second one is it is easy to perform differentiation and integration. We know that to do integration and differentiation of a polynomial function is very easy. And the third one is accuracy of the results can be improved by increasing the order of the polynomial. If you want higher accurate result, if you want better results, then increase the order of the polynomial. That may take time to solve, but we will get accurate results. For example, in the previous picture, we have seen polynomials linear and quadratic. In quadratic polynomial, we will get a better result. That is by increasing the order from 1 to 2. So far, we have seen the 3 steps in FE analysis. The remaining steps we will see in the next lecture. Thank you.